So we're going to do a quick video here on the half-life of radioactive substances. Half-life. And so this here is mostly just a nice little conceptual overview. The part where you have to actually really do some actual math and understand the formula and stuff that goes along with this is going to come later. It's just an HL topic, so we don't really need to cover that at this point, but we will later for the HL students in another little video. But essentially what half-life is when you have a radioactive decay. So let's say I just have some chunk of material here, and this isn't going to, it won't exactly split like this, but essentially if all of this stuff is radioactive and it keeps decaying, essentially we want to know how long does it take for half of it, exactly half of it, to decay. Now normally it would be kind of spread out randomly in there, but half of it gone. And we can do this a few ways. The main way is to essentially take a radioactive material and start counting its activity. Right? Have a little detector there and actually see how active is it. How much material do you have, how active is it, and then just kind of plot this over time. Come back every so often and watch it. Now, how often do you come back and look? Well, it depends. Is this thing so radioactive that it's going to be done in a day, or is it a million years? I just don't know. It just depends on the actual substance. But ultimately what will happen is you would take some measurements and some other measurements and some other measurements, and it would do something like this. It would basically, within uncertainty, it would give you this nice decay graph that would curve down like this. And mathematically speaking, it would never actually touch that bottom line here. It would asymptote down, but I mean, I guess in reality it's possible that eventually you get down in the very last molecule will eventually, but it just gets closer and closer, and the very last molecule could finally decay and it could go to zero, but for the most part it just curves right down like that. And so if you wanted to figure out the half-life from this, you just pick a spot on the graph and you look at the amount that it has here, say, I don't know, just any amount. If it was 100 here, 100%, you just go along until you get to 50%, and then you come across and you say, all right, there's 50% active compared to what it was. So if we count the initial activity as 100%, then we look and say, all right, when is it 50%? And you can just come down here and you look and say, all right, well, here was the time when we started, T1, and here was the time when we got to half of it, T2, and then you just find the difference between those times, and that would be the half-life. And if you came over here, you were at 50%, and you tried to go down to 25% then of the initial activity, then you'd come over here, and it would hit here, and you'd come down, and this would be time T3, and this amount of time that occurs here should be the same as the amount of time that occurs here. So every half-life that occurs, so from 25 down to 12 and a half, should bring us up here, and then again you'd get another time interval, and all of these time intervals should all be the same time. This should be the half-life of it, because each time you're cutting it in half. And so the idea is, if you're cutting something in half, how do you ever get to zero? You just keep cutting in half, 25, 12 and a half, 6.25, so on and so forth. You just keep going, and you never actually get to zero. It just keeps halving. And this is what happens, because this radioactive decay isn't based on, okay, this molecule will survive for this long. It's based on this idea of quantum mechanical uncertainty, where you don't know exactly how long something's going to live. You know that it has a 50-50 chance of decaying in a certain amount of time, and that's that half-life. So if I had 100 particles sitting here, and every one of them had a 50% chance of decaying in whatever the half-life was, I would expect that after that amount of time goes by, half of them would be done. The best example I've ever heard of for this was flipping a coin. So imagine you had 100 coins, right? And you flipped them all, and every time one came up tails, you threw it out. So you do your first series of flips, and you expect to get about 50 heads and 50 tails, which means you would throw out the 50 tails, then you'd have 50 heads left over. And then if you said, all right, now I'm going to flip these again, you would expect to get around, I mean not exactly, but around 25 heads and 25 tails, which means you'd throw out the 25 tails and you'd be left with 25 heads. And then if you flipped those 25 heads, you'd expect to get about 12 or 13, somewhere in there, of heads, or 12 or 13 of tails, depending on which it was, but somewhere around there. It might be 10 and 15, but it's just going to be near. About half of this would be tails. So let's say you got 13 tails. You'd throw out the 13 tails and you'd be left with 10 heads. And then you'd expect half of those to come up with tails. And you'd get rid of them and you'd be down around 6 or 7 heads now at this point. And then 3, and it would just keep going, cutting in half like that. So the first time you flipped, which was our first half-life, you had 50 of them come up tails, or 50 of them decay. And then the second half-life here, our second thing of flips, we only had 20. So here we lost 50, here, 25. Here we lost 50, and here we lost 25. But then look, as you go down here we lost just 13, or it could have been 12, or somewhere around there. But sure, losing 13, that's not nearly as big as our first set of flips where we lost 50 of them. And then in this last one, we'd lose only 6, and then possibly only around 3, and then around 1 or 2, and it would just, the amount you're losing just cuts in half every time, because it's a probability thing. It's a probability thing. It's not a this can only last for so long. It has a 50% chance of randomly decaying in that. So it models much closer to flipping coins than it does to really most other things you would see, where like if you had a plant sitting there that had a certain life, you can expect this plant to live 10 years, and pretty much after 10 years, if you had 100 of these plants, they'd pretty much all be dead at that point, because that's what it'd be. And after 5 years, they'd probably pretty much all still be alive. So it wouldn't be half. There wouldn't be really a half-life for something like that, because it's not a probability game like this is. So the main things you need to know about this are this decay curve. How do you read the half-life off it? Well, it decays down like this, and again, you just pick an amount, go to when you have half of that amount left, and look at how much time transpired between going to those. It doesn't always have to be from the maximum. You can go from 50 to 25 too, and it'll just keep giving you that same time interval as it cuts in half. And you need to understand that it's probabilistic, just like our coin flips would have been, okay? So it's very similar to coin flips and how that would work. And so those are your main things. And if you were going to do an experiment on this, that would be basically what you would do. You would come along, you would look at how much activity there was, you would make a note of it, and then you would come back a little while later and say, oh, now how active is it? And your points, of course, are not going to be perfectly on a line, because this is a probability thing. I mean, I guess there is still the chance that if you wait an entire half-life of this material, that nothing would have decayed. But that'd be like flipping 100 coins and getting all heads, okay, and not getting a single tails. It's possible, it's just really, really unlikely. I mean, really, 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 really unlikely. And then the more of these you have, because in these decay curves, you don't have 100 particles, you have millions and billions and trillions of them. Then this curve becomes very, very smooth, and your points really fit on the line very well. Because you could imagine if I went from 100 to, if I flipped 100 coins, I'm probably not going to get 50-50. I might get 55 to 45, and that's like that's a fairly significant percentage difference from the exact half-life. But if I had 100 million coins and I flipped them all and I only had 5 more heads than I had tails, then that's actually a very, very, very close percentage. So that would work out really, really well.